All right, welcome back everyone. This is going to be the last video for this chapter. It's going to be a quick video. Um, and I'm just going to cover the chapter section on the modifications in respiratory functions. Covers just a couple of interesting things. And then very quickly, one slide on embryonic development of the respiratory system. I'm never going to ask you guys to know too much about the embryonic development of these systems that we're talking about because wow, yeah, there's a lot of information already, and that's just one that I'm not really ready to focus on with you guys. So, um, first, there's two types of breathing: hyperpnea and hyperventilation. And so if from the outside they might look sort of similar, but the physiological effects are different. So the first is hyperpnea, and this is the increased depth and rate of ventilation that you'll see people doing when they are doing exercising, or they might have some sort of disease, but it's increasing that rate of breathing to meet an increased oxygen demand. Okay, and that's important. That really is what makes it stick out from hyperventilation. Um, that doesn't significantly alter blood oxygen or carbon dioxide levels, but what it does is basically increases the depth and the rate of ventilation to meet demands of the cells. So you're not changing too much. It's just that your cells need more because you're doing more work. In contrast, hyperventilation is an increased rate of breathing that is independent of cellular oxygen needs, and that will lead to abnormally low blood carbon dioxide levels, which in turn will decrease the number of protons, which actually decreases the pH levels, so which lead to high blood pH. So decreasing decreasing the number of protons actually increases pH, because you remember the more acidic is the lower number on the pH scale, the more basic is the higher number. And obviously you don't want your blood being either too acidic or too basic. And so if you're doing a lot of hyperventilating, which means that you're doing a lot of breathing and your cells don't need it, there's only bad things can come from that. So, and lastly, I just wanted to talk about this interesting thing is that hyperpnea isn't actually caused. Well, sorry, exercise doesn't actually cause hyperpnea on its own. And so you might be curious what that means. So when you start to exercise or you're playing a sport, you know that you start to breathe deeper and heavy. That's hyperpnea, right? But what we found, or what scientists have found, is that your hyperpnea, or that breathing, actually kicks in before your blood oxygen levels decrease. And so it's interesting because your body, if it was only due to needing more oxygen, you shouldn't kick in this hyperpnea before that need is demanded for. Okay, and so what this points to is that that's either happening because, so in addition to the demand. So one thought is that when you make a conscious decision to do something that's going to be an exercise or playing a sport, that also does some work in your brain that kicks in neurons that say, okay, we need to start doing hyperpnea. We need to start breathing deeply to get ready for this demand that we're very soon going to be facing. Or it could be independent of it, but I kind of believe that it makes sense if it's working in tandem, where your conscious decisions are kicking in other subconscious processes that increase your rate of breathing, and then you get this demand for oxygen from actually doing the work, and it just goes hand in hand in doing it. But I just thought it was interesting that exercise alone is not what causes you to do this fast breathing. Um, Let's talk about one interesting other little tidbit: high altitude effects on our blood and our breathing. When you probably have heard about athletes going into places that have increased altitude, and they have to do a lot of training for it, and also go there and sort of acclimatize for sometimes weeks at a time to get ready to do work in certain areas. And the reason for that is because if you increase your altitude, that decreases your atmospheric pressure. And although the proportion of oxygen that's in the atmosphere, it still remains, the same anywhere you go. It's the partial pressure that decreases, and you know that getting oxygen into your blood is all about how the atmospheric pressure compares to your interalveolar and your interpleural pressures. So as a result of that, it's more difficult for your body to achieve the same level of oxygen saturation at higher altitude than it is at lower altitude, because there's that lower atmospheric pressure. Normally, you want it to be higher than what it is on the inside of your body, right? Um, but so anyway, in fact, you'll see like hemoglobin saturation is lower at high altitudes compared to hemoglobin saturation at sea level. They give the example that hemoglobin saturation is about 67% at 19,000 feet, where it reaches about 98% at sea level. And so just pretty interesting that I'd like to talk about. What does this lead to? Altitude sickness, also called acute mountain sickness, AMS, but I've always heard it called altitude sickness. You might have heard it called that. It's a condition that results from acute exposure, or just high or long exposure to high altitudes due to that low partial pressure of oxygen. And that can occur typically at 2,400 meters or 8,000 feet above sea level. It's this result of the low blood oxygen levels, as the body has a real difficulty adjusting to the low partial pressure of the oxygen in the atmosphere. If you have a serious case of it, it can cause pulmonary or cerebral edema or swelling. You don't like that. The symptoms include nausea, vomiting, fatigue, lightheadedness, drowsiness, being disoriented, an increased pulse, having a nosebleed. And the only way to treat it is to descend to a lower altitude. But there are some pharmacologic treatments, and also taking oxygen through a mask can improve symptoms. You can prevent these symptoms by ascending to the desired altitude slowly, allowing your body to acclimate, which just basically means laying low, not doing a whole lot for a couple of days as your body gets ready, and also maintaining proper hydration is important. Okay, so let's talk about the embryonic development of the respiratory system. The development of the respiratory system begins at about week 4 of gestation, and by week 28, enough alveoli have matured that a baby that's born prematurely at this time can usually breathe on its own. So just remember, there's 4 weeks in a month. So the respiratory system, however, it's not fully developed until actually early childhood, when you get a full complement of the mature alveoli. And so really that's all I'm going to ask you to know about the embryonic development of the respiratory system. And that's going to conclude it for this week. So I'll see you in the next one.